yes, the title of my talk is A Guide to Shopping for Ontologies, which is maybe a little bit cryptic, but I had a kind of analogy in mind, which was that if someone were to ask me to recommend a laptop to them, I wouldn't just suggest buy this one no matter what. As an ontologist, my answer would always start with it depends, and then probably some advice on like what features to look into, depending on what they want to use it for. And so, in a similar vein, this talk is about recognizing a couple of design patterns in ontologies, which come about from how they're intended to be used, and kind of understanding that and recognizing that for using different ontologies for kind of their ideal use case. So in more detail, I'll be covering briefly what an ontology is and some related terms. So named vocabularies, taxonomies, and ontologies, and how all of those help create fair data. And then I'll be looking into two main ways in which ontologies get used, one which I've called external knowledge graphs, and the other one is linked data schemas. Those are probably a little bit less official terms, but they're useful. It's always useful to give something a label. And then looking in both of these cases how their intended use can shape their design. But I won't be going into recommending any specific ontologies. I'm hoping to provide you with a guide of kind of what to check and how to identify these design patterns. Okay, so starting off with named vocabularies, they're essentially a fixed set of terms with definitions, which is super simple, and so simple that I actually don't have great examples of things that are only named vocabularies and not also a taxonomy or an ontology. But similarities can definitely be drawn with any kind of dictionary or an enumeration class in programming. And I think as Dario was mentioning in his previous talk, these can be really helpful for making data more findable by restricting options down to a smaller set, or by mapping a larger set of expectations down to a smaller set of unique values. You can make it much easier for people to find data because they no longer have to try every possible term for something. The typical example for this would be if you had data, say, about species, then sticking to scientific names means that people know what to search for. Or alternatively, mapping all of the common names to the scientific names and even common names in different languages to some unique ID. That resolves to a single value, helps for searching for data. And then when comparing data from different places, reusing the same term avoids a need to create mapping between data. I personally find that most projects these days that I work on involve kind of mapping data from one place to another place to another place. And so anytime when I don't have to do that, that's a win. That speeds up my work. And finally, for data reusability, hopefully the terms should come with clear definitions, or at least clear in the context of the subject domain of the vocabulary. As a non-biologist, I am often finding myself a little bit lost, but I'm sure that the terms mean something much more to the experts who are reading it. And you know, one of the main kind of points of fair data is that you're not always there to explain your data, and these terms come with explanations themselves. Okay, so taxonomies, they're the next step up in complexity. They're a named vocabulary with some subsumption property, which forms a classification system. So by subsumption property, I generally mean that some set of things has been defined to always be contained within some larger set. So the set of all humans is included in the set of all mammals. As examples, you have the NCBI taxonomy, or you can find taxonomies powering kind of the navigation of most shopping websites. So products get classified in order to be structured under the main navigation. And with that, there's an obvious benefit for findable data. If the categories are clear to a user, it allows them to sort of navigate all the information to find the data that interests them more quickly. And then with something like search, related values can also be found. So a user doesn't have to do the work of searching for every single term. Let's say they're interested in all the information about a genus, then maybe they can search for that term and receive all the information that's tagged at a higher level of specificity. And when it comes to combining data from multiple sources, those sources might not have the same level of precision, but these taxonomic structures can be used to join up data in logical ways. And finally, onto ontologies. It's taken a few minutes, but we're there. They're generally a taxonomy with many other properties that provide a way to describe various links between concepts. So some examples are all the various ontologies that you can find in the ontology lookup service, everything that Dario has been analyzing and showed in his talk, as well as things like schema.org, the Dublin core terms, and Wikidata. If you're not familiar with Wikidata, on any Wikipedia page, there's often boxes on the right-hand side, and those are generated from information from Wikidata. And it contains both the information for that particular page, but also the definitions for the fields that appear on every similar kind of page. So this is from the page for France, and you'll see similar tabulated information on any country page. Okay, so with more properties, we're extending the ways in which we can traverse data and find related information. So if you think about, if you're Googling a film, you tend to quickly find links to other films in its series, as well as the cast members and the directors, and ontologies are supporting that kind of wider set of connections than just a pure taxonomy. Along with this wider set of description for connections, it's also possible to express inference rules and validation rules for data that follow certain patterns. So you can start off with a small set of data and generate additional information for free. And you can make sure that data can be used by other systems by following the validation rules to make sure that if you hand it off to someone else, it will work with them. And ontologies typically, hopefully, have some definitions with their properties, which again allows people to understand what was intended, the meanings of the connections that use them, and also provide more meaning to the classes that exist in their terms. So I've built these three terms kind of one on top of each other, but just because something's an ontology doesn't mean you can just choose to ignore all the properties and just use the terms as a named vocabulary, for instance, or just use the subsumption hierarchy and use it as a taxonomy. The advantage of reusing more parts of the information in an ontology comes at the potential cost of having to integrate with the data model being used to define that ontology. So there's often cases where just having the fixed set of terms gives you most of what you need to reap the benefits. And it's not worth going to the trouble of fully integrating with whatever data model you're using. Okay, on to the first use case. A typical design pattern is using ontologies as an external knowledge graph. And I say for free because of those trade-offs that I just mentioned. Depending on what you're using initially, you might need to make some changes to fully use it as an external knowledge graph. But here I've grabbed an image of an ultrasound of a liver and a tiny amount of JSON data to describe it. And instead of just using the string liver, I've picked a term here from the foundational model of anatomy ontology. And this term is linked to many other terms in the ontology. And you can actually see in the picture, this right kidney is to the left of this liver, and helpfully that is also covered in the ontology. The liver is direct left of some right kidney. And there's also other piece of information about kind of what kind of an organ it is and what constitutes a liver. And all of that could be used to allow users to search for different things and come up with other pieces of information. The idea is that, in a way, by reusing that one term, that reference to the liver in this ontology, you can jump from this small set of data that you control into this graph, traverse it how you wish, end up in useful places, and end up with more information than you started off with. So how to spot something designed for this purpose? These ontologies typically have a very large number of classes compared to properties. So FMA has about 100,000 classes, but only 168 properties. This is because while they use properties in the descriptions of classes, there are typically much fewer kinds of descriptions than there are things that need to be described. As a note, a lot of the time, these statements often aren't shown on ontology browsing websites. You tend to see the class hierarchy and the property hierarchy, but to get the kind of wealth of connections that exist in them and to browse that, you typically need to look at them using some kind of ontology tool like Protege, or if you're willing to subject yourself to that, look at the actual OWL file and read that as kind of quite raw data. And the other thing with these ontologies, they'll typically be very focused on a single specific domain. So FMA, for instance, is only focused on human anatomy. Now, if you're looking to use an ontology this way, the main thing to check for is, does the set of terms contain what you need? And you'll likely be checking the classes and perhaps a few key connections that you need. It's especially the classes that you'll be checking if you're intending to use it as a named vocabulary. You won't really have much use for the properties. And then it's useful to still check how those terms related to one another if you're using them in the kind of more taxonomic or more ontological use cases where you're actually going to traverse data. But it's also sometimes helpful to look at properties to get more understanding of what the classes actually mean. So checking the meaning of the properties, how both the classes relate directly to one another in the taxonomy, but how they are linked via properties, and kind of what assumptions have been made behind all of these links. And it's definitely a good idea to consider how you are going to link to these terms, especially if you're extending your own knowledge graph and you're using them in a way that the data models are closely aligned. Because the advantage of this is that you're getting a bunch of information for free in this case, because you don't need to do work to kind of align the data models. But it does come at the risk that there are assumptions that have been made and the information you're getting for free doesn't align closely with your intended use. So I'll explain that in a little bit more detail. Basically, if you're wondering how you should link to those terms, the answer is, as usual, it depends. So the classes in FMA are usually described as subclasses of some relation and class pair. And this means that if you have an inference engine, the rules that are laid out, and this is the bit that's probably the most technical, or I need to spell it out as correctly as possible. So the rules that are laid out here are that if you have something that is an instance of the class liver in the FMA ontology, you can infer that it is the direct left of something that is of the type right kidney. So this would be true, hopefully, for my body, and that my liver is to the direct direct left of my right kidney. Um, but you can quickly get into exception cases that you can think of. I mean, first of all, if you've got anyone with the genetic condition where all of their organs are right-left swapped in their body, that's not true. But also, as soon as you remove a liver and take it somewhere for imaging, etc., and slice it up, it's also no longer true. Um, so there are assumptions behind this ontology that are being made that it's describing a kind of Platonic ideal or exemplar adult human body. And so if you're using the instance of relation to, or the RDF type relation to make this connection, it's perhaps making assumptions that are a little bit less useful, or that at least might mean that someone else who's also using it in the same way has maybe made different assumptions than you have when it comes to sharing data. And that's fine. It's just suggesting that maybe as a user, you will need to come up with your own definitions for how you are using those terms, because FMA doesn't provide, it's focused on its use case of human anatomy. It's not focused on any use cases outside of that or how you are trying to reuse that. So yes, kind of linking into how you should link to these terms is the next use case, which is using ontologies as linked data schemas. And this is more in the world of linked data APIs, and they get used in a slightly different ways to the previous one, which is they're now mostly being used to provide definitions and structures for terms seen in an API's response, especially the fields. So this is an example JSON LD document in the center, but there are other ways in which you can return linked data. And so the idea is that you start off with this document here on the left, and you can add a context to it, and that context provides links to terms in ontologies that define what the field means. So in this case, the field subject has been mapped to schema about, so schema.org/about. And if you go to that URL, you can find a definition to say, oh, well, whatever this object is, this image object, it is about some, in this case, the liver ID that we saw previously from the FMA ontology. So an ontology that has been created for the purpose of kind of linked data APIs, it would likely have much more similar counts of properties compared to classes. Dublin core terms, they have 22 classes and 59 properties. Schema.org has about 800 classes and 200 properties, so still more classes, but much more similar compared to things like FMA. And the properties tend not to be used in the ontology itself as part of class definitions. So there'll be indications of what values are to be expected, or what types of things should live at either end of a property, as you would also in an external knowledge graph case. But you won't get those definitions along the lines of the kind of liver being to the direct left of the right kidney. And so in this case, when checking whether a particular ontology will cover your use case, you're again looking at the terms, making sure that what you need is there, but you're probably looking at the properties mostly, because in general, you have a lot of fields in a given API response, so you need to find properties for all of those. And then secondarily, it's useful to look at domain and ranges. That will tell you how the property is intended to be used. And if it's a kind of strict ontology, maybe things like disjointness or any other validation rules that you may be getting for free, which is always helpful, but it's also a very strong indicator of how the property expects to be used, and so how other people might be using it. Because yes, at the end of the day, especially in this use case, when you're sharing data, other people might be using these terms in their own use cases, and in order to actually make the data interoperable, you kind of need to be coming from a place of at least vaguely similar assumptions on how these properties should behave. Okay, and then there's just to note some further topics, since this has been quite a whistle-stop tour. There's lots of, yes, there's other ways, other aspects to consider, such as kind of maintenance and update patterns to ontologies. There's lots of other use cases for knowledge graphs that I've really not touched on. And just to add to the list of assumptions that I've been making, I've mostly been talking about RDF based ontologies. That's often the standard, but there's many other ways in which they could be organized. At least NCBI taxonomy, I don't think uses RDF, but also not only for writing ontologies, but also knowledge graphs, for instance. There are other technologies out there. And that's all. Thank you very much for your attention.